So here's two sets of numbers. There is a subtle difference between the two. 3, 6, 9, 12, 15, and then the other one is 3, 6, 9, 12, 15, dot. What's that? Yeah. This one stops. Huh? This one stops. First one stops. The other one goes on. So you have what are called, sequences. You don't have to write all this out, but I want to explain to you what they are. Sequences are basically domain and range. The domain is the number in the sequence, not like 3, 6, 9, but position. First number, second number, third number, and so on. Then the actual range of it would have been 3, 6, 9, 12, 15. So what we have here is what's called a finite and an infinite. It's finite because it ends. There's no dot. It tells me that there are 5 numbers in the sequence. The second one, with that dot, is called an infinite sequence. It just continuously goes on and on and on. Whereas what we're talking about is you've got first term, second term, third term, fourth term, fifth term, so on. Where these values, what we're going to call n. Number in the sequence. So this is your nth term, if you will. A lot of times you'll see it as a sub n, the number in the sequence. So the third number here would be 9. That's kind of all that is. All right. It's pretty easy once you understand the nomenclature of how this looks. It works really fast. Excuse me. Yeah. We'll talk about how we write these things out. We'll talk about when we get into sequences and series. Basically, what we have is the general stuff. We have arithmetic, geometric. That just doesn't mean it's star, star, square, star, star, square, star, star, square in terms of geometric sequences. Thank you. Hey, congrats! I saw you like won some big thing and you're really fast.
Oh, thank you.
That's awesome. But not what it's what the school record. And then infinite sum. Yes, we can actually find the sum of an infinite series. Weird. Numbers 1 for infinity. How do you add them all together? There's a formula. It's pretty cool. Do I need to even talk about this? It's very difficult. But you know what? Should you ever get a question like this wrong?
Yes.
Why? Because you don't use your calculator. Don't you have a fancy button on your calculator that says y equals? Yeah, remember that? So let's look at this. If I want to write out the first 6 numbers in the sequence, and I want to go to my y equals button, basically all I'm going to do is put in that formula, parentheses, -2 to the n minus 1. And I go right to my table. If I'm looking for the first 6 digits, the first 6 numbers in the sequence, I'm just looking at basically starting at number 1. Here's a sub 1, a sub 2, a sub 3, and so on and so on. That's all that is. Should you ever get a sequence list problem wrong? No. Especially if you're given what's called the rule. That -2 to the n minus 1 is the rule. Now, it could ask you what's the 15th number in the sequence. Well, that means n is 15. I know, I'm asking a lot. I know, it's a lot. So you would just scroll through. You get 16,384. Like you did. Okay. I know this is not trig, so are you guys okay with this so far? It's weird. We're not talking about sines and cosines. We're okay? All right. Trig did nothing to you.
It did everything.
I had to drop my grade a little bit.
Yes. Let's talk about where it gets weird.
Why?
Describe the pattern, write the term, and write the rule. So what we want to do here is write some rule that generates that. It's negative 1/3, 1/9, negative 27, 1/27.
Negative 1/3 and
N? What do you mean? Times n or? So if it's negative, you're saying this. Now, here's what we can do. If you say that's what you're looking at, how could I verify it if you're correct? Exactly. Go right to your table then. If that's what what you think might be. Go to your table, y equals, and type in what you say is your idea. So it's negative 1/3 n. You can leave it as a fraction like that, it's not a big deal, because it's just one singular value. So if I go to my table then, so I'm going to my table, negative 1, and that's not what we're getting, is it? No. What's that? Negative 1/3 to the n. Okay, let's try that. See what I'm getting at here, guys? You get a rough idea of what it might be. Use your table to help verify if you're right. So it's a little guess and check. So let's try it to the n. Did your calculator, if you use a fraction bar, spit out fractions? I wonder if that would help. Let's do this. Yeah.
So it does matter.
And a lot of it does work out. So in this case here, my rule wound up being negative 1/3 to the n. Now, what I want you to notice here is, this is a kind of a good idea to remember. See how your first term is negative, second term is positive, third term is negative, fourth term is positive. That means if you start just looking at that, in order to alternate between positives and negatives a lot of times, it means you're multiplying something together, or you're squaring it, or some power, because even powers, negative, negative, positive, and so on. Now, if it was the opposite of that, if it was positive first term, negative second term, and it went through, what you could do is throw a negative 1 in front of it, and then multiply it through. So there's a little bit of playing around with some numbers sometimes to see exactly how you're able to generate these patterns. Okay? So it wasn't negative 1/3 times n, it's negative 1/3 to the n. All right. Not bad. Takes a little time to get used to this. All right, what about 2, 6, 12, 20? 2, 6, 12, 20. Sometimes it's easier to write it out as domain and range. So if I know my first one is a 2, second one is a 3, third one is a 12, fourth one is a 20. Sometimes it's easy to write it out in terms of domain and range. Oh, sorry. How does a 1 generate a 2? How does a 2 generate a 6? How does a 3 generate a 12? How does a 4 generate a 5? The 20. What do you think, Jack?
Well, to do it like 2 or 6 minus 2 is 4, and 12 minus 6 is 6, and 20 minus 12 is 8. So like, wouldn't it be like adding?
But if you're saying it that way, then I'd have to be adding the consistent amount each time. Am I adding, it goes 4, 6, 8. It's not going to be an addition thing. Addition, that's going to be what we call arithmetic. And if there is an addition style, it would be common for each term. In this case, it's not. What do you got? Okay, so you multiply by 2, by 3, by 4. Okay, I correct. So how would you write that out in terms of ends? What's your first number? What's your first number?
But 12 times 4 is
Think of this as your n, and this is the,
like 1 times 2 is 2, 2 times 3 is 6.
so 1 times 2 is 2. You're saying 2 times 3 is 6. 3 times 4 is 12, and then 4 times 5 is 20. That's what you're saying, correct? Now, how can you write that in terms of ends? Perfect. Everybody hear that? N times n plus 1. And that's where understanding, you can find patterns. You're right, Chap, you're right, you're adding even intervals. You know, what was it? 4, 6, 8, 12 might be the next one, and so on. But how do you write that in terms of a general rule in terms of first term of the sequence generates this, second term of the sequence generates that, and so on. And that's what just takes time to get used to. Okay? Okay? All right. Kind of weird. Now, difference between a sequence and a series. This is another really, really, really difficult thing to spot. Sequence, 3, 6, 9, 12, 15. Series, trust me, this is tough. 3 plus 6 plus 9 plus 12 plus 15. What's the difference? You're adding. I know. Okay. A series is a sequence that you add each consecutive value to. Okay. The series notation is where we introduce you guys to what's called summation. Summation notation. Summation, that is the Greek letter sigma. Sigma notation stands for sum. Sum means add. Summation notation. You're going to find the sum of a bunch of numbers between starting at the first term. Usually we write it like this, where n is the first term, and you're adding it up through how many terms are in the series. Well, here we have 1 little, 2 little, 3 little numbers, 4 little, 5 numbers. I'm going to add the first 5 numbers of some sequence derived by, well, this was 3 times n. 3 times 1, 3 times 2, 3 times 3, and so on. So, guess what? There's a button on your calculator. I know. It's crazy. It's called summation. I believe. I think it's alpha zoom. Oops, button. Is it alpha zoom? Nope. Function. Yeah. Alpha zoom function 2. Alpha zoom, move to the left, and we go to summation. And see how it puts in a whole bunch of cursor spots. Now, obviously your calculator doesn't have the N button, but we have X. So if you want to use X's, that's fine. We know that the first value would always be an X. This next number is which value are you starting at? Are you starting at the first term, or are you starting at the 6th term? You're only adding up through 8, whatever. It's basically you're copy and pasting whatever you write here into this. Now, here you just type in a 1, arrow up, you want to go through 5, arrow in of your formula of 3x. Press enter, and it does it for you. Now, a lot of these things are pretty quick. You probably could have typed in 3 plus 6 plus 9 plus 12 plus 15 in the amount of time that it took you to type that. But for some of them, where you have like this crazy formula, yeah, just press the buttons, the calculator does it for you. Yes, ma'am.
Where did the five?
How many numbers are in the sequence?
Oh,
Or I'm sorry, in the series. There's 5 of them in the series. We're just adding up the first 5. Okay? That's where that comes from. Now, the difference between this and an infinite series is that an infinite series just keeps going. An infinite series goes through infinity. Now, I want you guys all to look on your calculator right now, and believe me, there is no button on the calculator for infinity. It does not exist. Okay? There is no button for infinity. No. There is no button on your calculator that does infinity. So you cannot put an infinite series in your calculator. You can't do that. Okay? Later on, we will talk about what you can do.
So right now we're just digging on.
Just ignore it, yes.
imaginary numbers.
Yes. Your textbook does use this. They'll use I, N's, or X's.
Letters.
This does not matter. It's not imaginary. It's just a letter. It's just a letter. That just means that the formula had like 3i to the 5th or something like that. Why they chose to use I in here is beyond me. Kind of silly, but it happens.
Imaginary numbers.
There is no imaginary numbers. Don't worry about it. We're not worried about any imaginary
Saying
numbers.
necessarily with imaginary numbers existing.
Yeah. See how what I mean here?
Yeah.
The example in the book, they use the I value instead of using N's. It's don't worry, we can see it. All right. So let's try this. Let's write this series. Let's figure out how many terms are in the series. Let's figure out what the rule is for the series, and then how do you write it in terms of the series? We want to write out the whole thing in terms of this summation notation, which means we'll use sigma. So if I start with the series of 5 plus 10 plus 15 plus something plus to 100, first thing you got to figure out is what's the pattern. It's 5n. 5 times 1, 5 times 2, 5 times 3, and so on. Are we okay with that? So we know the rule is going to be 5 times n. Where does n start? Is n going to start at 0? N going to start at 1? Is n going to start at 2? Can you adjust all that? Yeah. Could I say that this is 5n minus 5 if n starts at 2? If n starts at 2, isn't that 5 times 2 minus 5, which equals 5?
So this is another one of those
5
things.
times 3 minus 5, which is 10. So I could do it that way too. There's multiple ways to write these formulas out. Now, would I want to do it this way?
If you really feel like it.
I really wanted to, but that's just kind of silly.
So it's 5n minus 25.
Yeah, exactly. We'll say n starts at 1. And how many times do you have to multiply 5 by to get to 100? 20. So this is an example of when you do not want to try to type all that into the calculator, 5 plus 10 plus 15, and do that all the way up to 100. That just is silly. But if you use summation notation in your calculator, you'll spit out an answer and you get,
100.
don't you think it'd be more than 100?
If there was, I thought it was 20 terms.
Yeah,
Five
yeah,
times
5 plus 10 plus 15 plus, you're already going to add it to 100, so I don't think it's going to be more than 100 no matter what.
Adding it all.
What is it? 1050. That's like 9. I know, they're not very good. How's your foot? Good conversation. Try to be caring, show that I'm not just a robot. All right, let's try this one. What are you laughing at? What's the pattern? Look at the relationships between the numerators and denominators. What's the pattern? The the denominator becomes the numerator. Okay. Each one of them is going up. Numerator goes up, denominator goes up. Yeah. Watch what happens. If I start at n from the top, isn't n plus 1 the bottom? It's sometimes so blatantly obvious you overlook it.
This is the trick. Now you're just thinking in trig and everything's 2 separate.
Yeah, you're like, wait, 1/2, that's gotta be a 45, 45, 90. Where do I start this problem at? Start at n equals 1. Through what? Where do we go to? To infinity. And beyond! The hyperbolic paraboloid. I told you guys about that before, right? Really?
Of course.
I never told you guys about the hyperbolic paraboloid?
Yeah, you know.
It's a Pringle.
Yeah.
Pringle chips. The Pringle chips are a hyperbolic paraboloid. The guy didn't like having crushed potato chips in the bag all the time, so he made them out of stack. Because you know how arches are one of the strongest structures? Did you know that?
Pringles aren't very strong.
I mean, there's
They still,
They're
they still,
last in the can, this way they don't get a bunch of crumbs at the bottom.
but they still can get crushed.
They still-
But
They
It's
break
a
so
lot
easy.
harder.
but they're more rigid than the other stuff. But that's where the guy
If
that
you
was a
had
mathematician.
flat chip like that, it would be it would break easier than regular
Yeah, the guy that invented the Pringle was a math guy. He was sick and tired of chips breaking, so he developed a way to press the chip into what's called, this is an 85 rule. This is not a 15 one.
I would
This
say
is
that-
called a hyperbolic paraboloid. It's a conic section.
That, a
you should
Dorito
bring up
is
Pringles
more
together.
durable.
Well, Dorito is more of a corn chip. Corn chips are generally thicker than a potato chip.
If you compare I can't say it.
If you put a different kind of chip into the Pringle box, it would most
Like
likely
Lay's.
crack.
So you're right. Now, I really want a Pringle right now. So,
They're still chips, so they.
can I put that in my calculator though?
But they
I
don't
can say it's slow, but as soon as you try
speed.
No, because where's this button located? Not on the calculator. You have no idea how many of you guys are going to ask me, where's the infinity button? That's exactly how you guys sound.
I can't help it, I can't say it. I can say probably.
Do I need to show you how to press this in the calculator? No, good. Do I need to show you how to push this in the calculator?
Yeah.
No. Do I need you guys to memorize special formulas for series?
No.
No. You know why?
Because they're all the same.
Because there's a button on your calculator. Is there any reason why you would just put this in the calculator? Am I going to take the calculator away from you? No. I could take it away from you, you'd have to know how to do all this, but isn't that just kind of silly?
This is cool.
Yes. So, could you put that in the calculator? Yes. Could you put that in the calculator?
No, we don't have a cake button.
Yes.
I can't say probably.
There's one of these I need you to skip because I can't even. One of the rules is
That
just
technically
awful.
is chip cutting though. Like I feel like everybody has like one word that they can't say.
Do not do 23. No 23.
Wow. Maybe you should have been like a foreign language teacher.
That would have been funny.
You just now know that you just now figured out that I know Spanish? You've been in my classrooms 2 years. How much Spanish have I talked within 2 years? La puerta está allí. No baño aquí, por favor. Es un reloj. Los zapatos negros.
I just heard.
Sí. Hola, yo también.
Yeah, that's it.
Café es muy bueno.
Next year you should get like all these just switch classes for Tuesday and just not acknowledge it when students ask about it.
Hola.
It's like, what are you talking about? I've been here all year.
Hola, ¿cómo está usted?
I've been your teacher all year.
It's like the prank on The Office where Jim becomes the other guy.
yeah.
At the very beginning one, where they switch out. What are you talking about? I've been here all along. He's like his actor friend. He's got the picture of him in
Yeah.
was it Jan. Is that the wife? Jim. Pam. Pam.
That's close enough.
Pam, Jam, whatever. Jan.
And
Sorry?
Yeah, I put it in there. I figured we'd mark it into 3 of them that way.
I also read Jim in white.
Yeah, trig stuff. Once we get, I think Emma still has to take that. You know, she was in New York touring with all the fun people. So hopefully she'll get that tomorrow.
Yes, tomorrow,
We'll do that tomorrow. And then,
why would you
what was the other? The rest of we'll talk about it. I think yeah, I don't want to give anything else away. There was a couple of you guys went way too difficult on some of the simplify verify, and then some of you guys went an even shorter route than I did. And I was like, oh, I was impressed. I was like, oh, cool, that works. So there's a lot of, and then there were some people that just wrote down things trying to go, yeah, like just throwing a bunch of stuff on paper and see what sticks. So
That was me.
My answer was like,
That's
I
I sat there, I was like, I looked
so
at
bad.
it.
It was like, I was like, I'm like, I get to the very end, I was like, it doesn't work.
there was a lot of that, and
Wait, are we still skipping 23?
yeah.